Good evening, everybody. And today we're going to talk about how static analysis can help in quality assurance automation processes. But first, let me introduce myself. I'm working at Wrike for more than 3 years, mostly on our QAA framework and its quality. And I also like playing beach and classic volleyball. So in case you have any volleyball questions, you may ask me in LinkedIn or Telegram. I'm just kidding. You may ask me any questions about this presentation. Okay, here's the plan of today's presentation. We're going to talk about how we analyzed our code before, what made us think about introducing some changes, and in the end, I'll summarize how it is now. From my perspective of view, quality of a product comes with the quality of tests. Because we, as quality assurance automation engineers, work on improving our product. Writing tests decreases the amount of work required for manual QAs, and this decreases time to release a new version. This means that time to market decreases. But writing tests in a proper way is also important because it influences on several things, like the speed of development, how fast we're able to add new tests or to fix some old ones. Maintainability. It means that we're able to support our code base in a proper state. Refactoring is crucial when we have to do some massive refactorings without lots of manual works and timeless fixes. And sustainability. Sustainability means that our framework doesn't break into pieces with a small fix or new feature. Okay, let's dig into some dark ages when 3 years ago, we had from 10 to 15 contributors, and most of them were quality assurance automation engineers. And at that time, we had an informal set of coding guidelines. This meant that we had to repeat the same thing over and over each merge request. Please bear in mind, this is just a random screenshot to illustrate our state of those times, but I believe you understand the idea when you have to point out to some white space fixes and line length and so on and so forth. You may ask me, why was it bad? Why do you think that this previous example was bad? Well, you had to do a lot of repetitive tasks in each merge request in order to point to some small coding issues. Sometimes these numerous issues could distract you from real problems, especially when you have a lot of changes. And last but not least, your knowledge of informal rules can be outdated, and you have to refresh it from time to time and to ask your colleagues what's the correct way to write the code. This was the time when we decided to change something in our approach, and we decided to add an IntelliJ IDEA codestyle file. Basically, it's a set of guidelines applied in IDE, and it regulates an order of imports, byte spaces, line length, and so on. Also, this file can be distributed via version control system like Git or Subversion or anything else. This is how our custom code rule looked like. We decided that abstract methods could not be marked by step annotation. At this moment, we thought that our code base soon will be like this. But, you know, it didn't happen. What were the reasons? This approach has several disadvantages. The first one is that this code style file is supported only by IntelliJ IDEA. But the more important one is that this code style is not applicable for remote launches. We used it only for local launches, but we also have a need to be able to check code style on a remote launch, but more on that later. And this is where PMD comes on the scene. As Sergey already said, PMD is a static analysis tool that scans your code, and it finds your problematic codes and bad patterns that you usually put inside your code, and it generates violations, lots of them, especially when you run this library for the first time. Before doing some checks, PMD parses the source file into a data structure called an abstract syntax tree. This tree represents the syntactic structure of the code and encodes syntactic relations between source code elements. This means that every Java structure has its own representation in terms of this library, like method declarator, enum body, and so on. This AST tree is the equivalent representation and has the root node compilation unit. After this tree has been created and filled with additional information, the rules, so-called rules, are executed. So we applied a bunch of rules from PMD. By default, it has about 250 built-in rules. Moreover, we tweaked some options of PMD for our purposes, but more on that later. And at some point, we decided to go further with PMD because it provides a great opportunity to write your own custom rules. So when we decided to use custom rules, we wanted to solve two our problems: to standardize guidelines that are adopted in our project, like naming, usage of imports, usage of different libraries that are used in our code, to help us to mark up tests and test methods, which leads to the fact that correct markup allows us to evaluate testing pyramids. And you know, this is really important when you have more than 20,000 of tests. You may probably saw these slides in Sergey's presentation, but I want to emphasize those facts that each test has its own test case ID. It is our constraint, and using the same ID for several tests will produce some real problems, but I'm not going to dig into details. We just need this test case ID to be unique. That's why we decided to write a special PMD rule. And here we have to do several things. First of all, we have to extend our rule from abstract Java rule. This is a class that's provided by PMD library. Then we have to override method visits. It means that when PMD scans your file, your Java file, it will visit every method in this file, and it will apply all the logic in this method in order to check whether this method passes or it generates a violation. Here we just traverse all our code base to find out if we have a unique ID, and if this ID is not unique, we throw a violation. I promised to tell you about some custom tweaks that we made for our project. First of all, we run only changed files because we don't need to check all the code base in order to, especially in cases when you fix only 1 or 2 files. Then we found out that when we first implemented integration with this library, we scanned our files in a sequential way. Then we fixed it and made it to scan parallel. That's the reason why our runtime for all the projects decreased from 11 minutes to 3 minutes. However, we usually do not scan all the projects. As I already said, we can only change files. But, making things faster is always better. And we integrated this library into our GitLab pipeline. This is how it looks like. We have 2 stages in GitLab, and we have a compile phase and analyze phase. In case our analysis fails, we can see an incoming message in Slack with a mention, so that everybody will know that you write some bad code. Okay, I want to show some results. Right now, we have about 12,000 merge requests being merged into our repository, and we had about 350 merge requests last month. And during last year, we had about 100 active contributors. Just imagine and compare it with the some of my previous slides where I said that we had about 10 to 15 contributors. This is really tremendous numbers. And as you can see, we have a growing number of merge requests each month. And I believe that applying our custom rules and using static analysis helps us to maintain our code base. And right now we have about 25 our custom rules. And I believe this number will just grow up. That's all from my side. In case you have any questions, feel free to ask me here or to contact me in social media.